Hi, today we're going to present to you our project entitled Trajectory-Based Flight Phase Identification with Machine Learning for Digital Twins. Together with the University of Hamburg and the DLR Institute of Maintenance, Repair and Overhaul, we are going to present our project. My name is Amy Arts, and together with Alexander Kamtsiouris, we will show you what we've done.
Thank you, and hello from my side as well. Together with Amy, I'm working at the Department of Process Optimization and Digitalization. In today's presentation, I will focus on labeling the training dataset.
I believe that most of you are already familiar with flight phases or phases of flight. Although there's no specific definition, they represent the stages of the aircraft during its flight. So for our work, we focus on the taxi, takeoff, initial climb, cruise, descent, approach, and landing. And we would like to use these flight phases for degradation prognostics. However, there are several more applications that use flight phases, such as trajectory prediction, analysis of environmental impact, knowledge about the aircraft setup. And flight phases are either part of the aircraft's internal data or they're computed on this data. Now, internal aircraft data is very sensitive and contains a lot of sensitive information regarding the aircraft itself, or the airline or the pilot flying the aircraft. As such, this data is not often shared and has thus a very scarce availability to the general public. With internal aircraft data not often being available due to its sensitivity, however, trajectory data often being shared by the ADS-B concept and then distributed through different platforms such as the Open Skynet or Flight Radar, it is beneficial to identify a phase of flight based on the trajectory. Now, not every phase of flight can be specifically defined by its trajectory, but there is a clear relation to the trajectory and the stages of flight. Now, if we were able to identify the phases of flight based on solely the trajectory, so on publicly shared data, in our case, in the Institute of Maintenance, Repair and Overhaul, we could use this for validity check of our aircraft models, for the degradation prognostics, for example. However, other applications could benefit from this as well, such as air traffic management to have better flight trajectory prediction, or fuel consumption optimization, since different stages of flight or flight phases represent different fuel consumption, but also in a post-analysis to have more knowledge about the safety functions and switches that were put in place on the aircraft during its flight. There are several models out there that identify flight phases based on other variables. First of all, Paglione et al. Used a statistical approach to identify flight phases, and Kovarik et al. Compared their work to the statistical approach and found that machine learning yields better results for flight phase identification. Liu et al. Used a Gaussian mixture model, as such used clustering, which is an unsupervised machine learning task, to identify flight phases, and Sun et al. Used ADS-B data to identify flight phases. Now, all of these models exclude the takeoff and landing phase, which can often be essential for different applications such as degradation prognostics. So this is why we wanted to develop a model that identifies the flight phases only on ADS-B available trajectory data, and at the same time includes these shorter phases of takeoff and landing. More information about the flight phases will be presented later on. For our work, we base our approach on supervised learning. This means that we take the trajectory data of the aircraft and we augment it with the correct flight phase that we got from the internal aircraft parameters, and we use this data to train the model so that it can learn to associate certain trajectory patterns to certain flight phases. Now, the model consists of three main steps. The first step being pre-processing, where the data is indeed labeled and the flights are trimmed so that the model is not only able to identify a complete flight, but also partial flights. Now, these flights have to be represented in a way for the classification to be able to classify the pieces of the flight, and this is done by the segmentation. So each flight is divided into a sequence of segments, where each segment is represented by its features. Finally, this sequence of segments is fed to the classification neural network, a long short-term memory that then classifies each single segment of the flight, and the flight is then reconstructed from its segments with the correct label that the classification network assigned to it.
In order to automatically generate sufficiently sized training datasets with a satisfactory variety of trajectories, different flight data sources are considered. This flight data typically consists of different parameters such as various landing gear indicators, engine power parameters, and other operational parameters like altitude or rate of climb. In the case of the German Aerospace Center, real flight data can be obtained from the research aircraft. Generally, the disadvantage of real flight data might be bad availability, too small datasets, and even really biased datasets because of the specific missions a certain aircraft might be flying during its lifetime. Simulated flight data, on the other hand, is more easily adaptable and therefore minimizes the inherent biases towards specific missions. That is why we used the Explained Flight Simulator to generate trajectories. Using the ICAO Accident Reporting System's flight phase taxonomy, we labeled the flight data. A globally standardized vocabulary for flight phases and its criteria supports the integration of the developed tools in other aircraft research applications. Each flight phase is characterized by different combinations and boundaries of flight data parameters.
Once the trajectory data has been augmented with the correct label, we want to be able to represent the flight as a vector in order for it to be then classified by the neural network. Other works that I've presented previously opted rather for a time frame approach, which means that they, for example, took a 30-second time frame and identified what flight phase was flown within those 30 seconds without looking at the previous data. Now, we would like to argue that there are some dependencies during a flight where there are some temporal relations of its trajectory variables during the flight that have a high significance to the current phase of flight. So for this, we divide our flight into 160 segments, where then each segment is represented by its features. The features of a segment are the beginning and end altitude, the beginning and end speed, and the beginning and end rate of climb. As such, a flight is represented by a sequence of 6 features, and this complete sequence will be classified as a sequence by the neural network. Once a flight is represented by a sequence of segments, we want to be able to identify the flight phases flown on each of these segments. We do this by using a neural network, more specifically a long short-term memory network. Long short-term memories are a type of recurrent neural network, and recurrent neural networks are often used for sequences. Now, long short-term memories have the peculiarity that they are able to handle longer temporal dependencies very well, which is the case of a flight. So this neural network classifies each segment as part of the sequence. This means that for the classification of a single segment, it does not only take into account the features of that segment, as we discussed previously, but also the history of the previous inputs or the previous segments it has seen before. Now, early on, we found out that, of course, not every flight phase is represented by as many segments, because a shorter flight phase will be given by fewer segments than a longer flight phase. For this reason, we introduced a loss penalty function to address this problem called class imbalance. To give an incentive to the network to perform well on all flight phases and not only the longer flight phases that are represented by a larger amount of segments, we introduce a loss penalty function. A loss penalty function is added to the normal loss function. In our case, for the loss function, we used a negative log likelihood function. So the loss function generally represents the number of correctly identified segments and penalizes the neural network based on how many segments it classified incorrectly. However, by introducing this penalty function, we add a penalty to the loss that the network then also has to minimize. In our case, the penalty function consists in the average ratio of false positives and false negatives for each class or each flight phase. This is then averaged over the number of flight phases and multiplied by an influence factor alpha. This influence factor was then empirically found with a hyperparameter grid search, and we found that the optimal value is the value of 3. So this penalty is added to the loss function and allows the network to not only focus on correctly identifying each segment, but also focus on getting better accuracy on each of the single flight phases. The results that we show you are the average results of 3 instances trained independently for 3,500 epochs of both a model without penalty function and a model with penalty function, where with penalty function the influence factor alpha of the loss penalty was of 3. Now, when we look at the influence of the loss penalty function, we can see that it increases the recall at the expense of the overall accuracy and the precision. This means that the false negatives are decreased when using the loss penalty function. However, the false positives are increased. Now, in both cases, we obtain an overall accuracy of over 97%. This means that more than 97% of the seconds of flight were identified correctly with their flight phase label. But when we look at the single flight phases, we can see how especially the shorter flight phases, so the takeoff, initial climb, approach, and landing, suffer more inaccuracy than the longer flight phases. This could be due to several factors, such as the fact that the approach and initial climb are very hard to identify from the climb and the descent phase. But also, since the flight phases are short, if there is an overlap of different flight phases within one segment, this will introduce a bigger error to a shorter flight phase than it would to a longer flight phase. However, overall, the weighted accuracy, or the average between precision and recall, is around 91%, which is still a good result. In this slide, we can see the result of a flight, of a simulated flight, so recorded with the X-Plane simulator, and we can see how the overall accuracy is relatively good, and there are some minor inaccuracies at the edges between the flight phases. So in the transition between descent and approach, it's the largest error in this case. What we can also observe from this figure is that the simulated flights look a little smooth, more smooth than for those of you who have seen an actual trajectory from ADS-B. You can observe that this flight looks a lot more perfect, a lot more smooth, especially the rate of climb shows these very significant drops in the leveling stages in the descent phase. But also the overall transitions are much smoother, and there is much less noise than what would occur in an actual ADS-B flight. Now, overall, the flight phases are identified very well, and we hypothesize that if the model were to be trained with real flight data, that the results would transfer well to the real ADS-B data. On this slide, instead, we can see the results of the model trained with the simulated data, but evaluated on actual ADS-B data. This is a flight of the ATRA research aircraft for which we had the internal parameters available. And we can see that the accuracy is still fairly good. However, as is often the case in ADS-B data, the initial and final parts of the flight that are near to the ground are lacking. Which is why the training data was in fact trimmed to not always include all flight phases. And as I mentioned before, there are several differences when comparing both the simulated data and the real data in its behavior during the flight. So especially the rate of climb is much less smooth, much less predictable than is the case in the simulated flight. So it would be very interesting if there were someone among you that has the availability of a larger amount of flight data with internal aircraft parameters that are also recorded through ADS-B to then train the network on these real flights. In our case, we used 500 simulated flights for training and to evaluate the results when the network is trained on the real data. However, so far the results are still very satisfactory, and we hope that you can benefit from this model for your own research. Thank you for your attention. We would very gladly answer any of the questions you may have. If you happen to have some questions after the Q&A session in the conference, you can reach us at amy.arts@dlr.de or alexander.kamtsiouris@dlr.de. We're looking forward to any questions you may have and also some feedback.